if you want to ask questions, there we go. If you want to ask questions, put them on the chat room and we'll try and answer them as we have time. So John is an engineer here working on Apollo and beyond, and he's going to give us his discussion about what it means.
All right, well, I will share my screen. So everybody can see that okay? How do I get rid of this page?
It just kind of disappears.
Or this. Can I minimize this?
Yes. Yep. Mm-hmm.
All right. So you introduced me as an engineer, and that's certainly how I started out here at NASA. I got my Bachelor's of Science in Aerospace Engineering from the University of Texas. Because when I was in high school and I talked to my high school counselor about careers and jobs, we didn't really know a lot about the space program, but I wanted to work in this space program. And we thought aerospace engineering kind of sounded like a good job to get if you wanted to work in the space program. But when I was a little kid, you know, and going through school, my favorite subjects were science and history. And I loved being in the outdoors. And sometimes I wish my high school counselor would have known about planetary science and planetary geology. And maybe I would have gone into that straight away. But I did discover that when I started working here at the Johnson Space Center as an engineer, working with scientists on what they wanted to do on the moon. And it was so cool, I started to go to night school. So I worked during the day as an engineer. I went to night school to learn planetary geology. At the time I was married, we had 2 kids, so it was kind of a crazy time in my life. But it's been an awful lot of fun. These pictures on the bottom, the one where I'm in the red flannel shirt, that's out at Los Alamos. And those are big volcanic pyroclastic flows behind me, really, really thick. And then in the middle on the bottom, that's me standing in front of a big crater out in Arizona. But that's a big volcanic crater. It's called a Mar volcano, where magma coming up from below hits water, and then that water turns into steam, and then all that pressure creates an explosion. So we call those Mar craters. So that's a big Mar crater behind me. It's not an impact crater. And so, you know, some of the things, Paige asked me to put these little 3 things down, these 3 attributes of, you know, what has been important to me and to make my career successful, both as an engineer and a scientist. And of course, number 1 is be really flexible on what you can do, all right? And what you're open to doing. You can't really have a, you know, fixed mindset that I'm only going to do this and nothing else. You want to be flexible in everything you do. And a good way to allow that flexibility is to get a really good basic education in math, in science, in English, you know, history. You get a good basic education, and that allows you to be more flexible. And then, you know, what's really helped me here at NASA and, you know, got me in trouble when I was a little kid in elementary school is I have quite an imagination. So I talk a lot and I think a lot of crazy things, but turns out that's pretty a nice thing to have here at NASA, to be creative and imaginative. And in any career, really, you know, if you're trying to come up with something new for the very first time, whether it's space stuff or whether you're coming up with a new electronic gizmo, you know, to connect to the Wi-Fi or whatever, you know, that imagination and creativity will carry you a long way. So, you know, you can get a good basic education, be real flexible, have a lot of imagination and creativity, but if you don't work hard, you don't really ever get anywhere, right? So you always have to work hard no matter what you're doing in life, whether it's schoolwork, whether it's a sport you're playing like soccer or baseball, or you get a job, right? Like here we are at NASA being a planetary scientist. So you're always got to work hard to make meaningful accomplishments, because if you're just going through the motions and you're not really accomplishing anything, well, then what's the point, right? We all want to do something special in our lives. So how do I...
If you click on your slide, you should be able to get to the, click on it. Oh, there you go.
Oh, so I don't have to do the return button?
I don't think so.
All right. So when I was a little kid in elementary school, this is what I got to watch on TV. Now at the Gruener house, it was a black and white television. We didn't see all, the colorful gold foil on the bottom of the lander for, that's for thermal reason. That's like insulation. And the red, white, and blue of the American flag. On our black and white TV, it was all gray. But as a kid, this was really, really cool stuff. So, and people my age are all over the space program. And so it was Apollo that really, inspired us to do this. So here I am in the red tennis shoes with the arrow pointing at me. I'm about 5 years old. And this was my first day on the job at the Johnson Space Center. Well, not really. But it was a family visit because, I don't know, can you see my picture? So this was my Uncle Don, and he worked at NASA during the Apollo program. And he would bring us down to the Johnson Space Center and show us all sorts of cool stuff. And what we're standing in front of, this big dark room back there, is a huge thermal vacuum chamber where we could put spacecraft. So you can kind of see this spacecraft in there. You can put spacecraft in this big room, shut the door, and suck out all the air to make it a vacuum of space. And then you can make it either really, really hot, like the sun shining on it, or really, really cold to see if your spacecraft or your hardware can actually survive in that environment. And as a matter of fact, here's a picture of me at 5 years old. And today I'm 58, and I'm probably sitting about 200 yards away from this very building. So I'm in the last 5 years of my career, and it's ending just about where it started back when I was a little bitty kid. All right, so next slide. So like I said, when I talked with my high school counselor about what to work at NASA, we thought aerospace engineering. And when you go to aerospace engineering, you learn how to build spacecraft, rockets. If you stay atmospheric, you learn about airplanes and helicopters. The middle graphic there is trajectories from the Earth kind of going out to Mars, all right? And there's the sun in the middle. So you learn how to calculate these kind of trajectories from a circular orbit of the Earth, an elliptical orbit of Mars, and then you can calculate a trajectory. So you learn all that stuff in aerospace engineering. And so I was well prepared to come to work at NASA. But when I started working on missions to the moon or Mars, I also worked with mechanical engineers who designed things that would work on the surface, such as these cars. These are pressurized rovers, so kind of like submarines that would actually drive around on a surface of the moon or on Mars where you don't have much atmosphere, so it all has to stay contained in that vehicle. They build spacesuits. Of course, they build robots, all sorts of robots. Also worked with chemical engineers who want to take the dirt on Mars or the dirt on Moon and chemically break it up and then, collect things like oxygen and hydrogen and water and metals like iron and aluminum that we can build stuff. So I worked with a whole bunch of engineers on what would we want to do on Mars someday or at the moon, using the moon as a proving ground of how to work and live. And one of the things we had to do, of course, was talk to the scientists and say, well, what is it like on the moon? Because our engineering systems are going to have to work in that environment. What is it like on Mars? And once you kind of get an idea of the environment, then you start talking to the scientists about, well, what do you want to do there? Because, it's not so much the engineers that are going to really do anything on Mars. They're designing the things to work on Mars. It's going to be the scientists or the people who are trying to use these natural resources that want to do something there. So that was, and one more engineer we worked with. So civil engineers, of course, they do a lot of mining here on Earth. So we're going to do mining on the moon or Mars to get to those resources so that we can use them. All right. But I came across this quote as I was going through my career at NASA, where the crossing of interplanetary space is a huge technical problem, right? But it's not an end in itself. It's just a beginning. And then there's no point in going somewhere unless you do something when you get there. And that doing something was all of what the scientists were talking about when I was, talking to them about engineering things. So this was kind of where I changed my career to where I didn't really care to be an engineer anymore, because we had about 10 or 12,000 engineers here at the Johnson Space Center. What I really wanted to do was talk about more of what are we going to do on the moon or Mars and why, right? And so this led me to my career as a scientist. And so the field I work in is planetary geology. These are some of our co-workers here where, we will spend our time in the labs, like at the bottom. Andrea here is actually holding a moon rock in our curation facilities because when the Apollo astronauts went to the moon, they brought back lots of rocks and dirt. And so we saved those in special cabinets full of nitrogen gas so they don't change from the way they were on the moon. And then people like Kelsey right here, Kelsey Young, and Stephanie's actually an astronaut. We go out in the field and practice on how we might explore the moon again with new technologies, or how we might explore Mars someday, right? But geology is only one of the sciences. We work with astronomers, and I think one of the cool things is finding all these planets out there around other suns and other stars. And now we found about 3,000 planets outside of our solar system. And of course, the real fun part is, are these potentially habitable planets? And maybe people could live on these things, or other life forms are living on these things, right? So we work with astronomers, and of course we work with biologists because we got to keep our astronauts up here healthy and happy. We will grow plants in our life support system, so we'll have food to eat. And of course, through photosynthesis, plants give us oxygen to breathe, and through transpiration, they give us water to drink. So plants are going to be a big part of our life support systems. And then intriguingly, down here in the bottom, you see this little worm-looking thing. Some people in our building thought that was fossilized bacteria in a meteorite that came from Mars, right? And so if a rock that came from Mars has fossilized bacteria in it, what is that telling us about life elsewhere in the solar system or elsewhere in the universe, right? So the biologists have some pretty cool things they're working on, all right? So we're going to focus now on the moon, because that's what we're working on in a big way right now, getting back to the moon to do different things. But here you are in 30 seconds and on one slide, what we learned from the Apollo missions, all right? First, we found out that the moon likely formed when a Mars-sized planetary body was flying through space and it smashed into the Earth. Part of the Earth was flung out into space, and then that kind of accumulated. All those bits and pieces accumulated in orbit around the Earth, and then all those bits and pieces kind of came together to make our moon. And all of that happened about 4.5 billion years ago, all right? And this very old surface of the moon has been beat up by constant impacts from meteorites. Meteorites fall on the Earth, but meteors, asteroids, comets, all those things that have smashed into the Earth have also smashed into the moon, making big round craters like this guy right there. There's a big impact crater. Here's a smaller one, but they're all over the moon. Here's a bright one. So that's a lot younger, because you can see all the stuff that came out of this crater is laying on top of the older stuff. So this one here, that's a bright new crater, because look, all of the ejecta that came out of the crater is laying on top of the dark surface. So the lighter stuff came after the darker stuff, right? So it turns out that darker stuff on the moon is lava. It's just good old basalt. Covers our ocean floors, comes out of the ground in Hawaii, eastern Washington, all over the place. Matter of fact, basalt's the most common rock in the inner solar system. It's on Mercury, Venus, Earth, the moon, Mars. It's all over the place, right? So those are the dark areas of the moon. So big lava flows filled up some of these holes and created the mare regions. Mare is Latin for seas. And a long time ago, when people would look through the moon with little telescopes, they kind of thought those dark areas were like seas, just like they hear on the Earth, right? So the brighter areas are what we call the highlands, and it's a different rock. So maybe if you've done geology in your science class, you've done Mohs scale and rock hardness, and there's a mineral out there called feldspar. It's very hard. It's like 9 on Mohs scale. 10 would be diamond, so it's really, really hard stuff, right? But we think this bright area is like the original crust of the moon, right? And really, really old. So when you look up at the moon at night, you see the old, bright highlands. You see the younger, smoother mare. You see the craters all over the place that have battered the moon. And what that constantly impacting and beating up of the moon has done to all the rocks is it's turned it into dirt or soil. We call it regolith, right? So the whole moon is covered with anywhere from, 3 or so meters to maybe 15 meters deep of this dirt or this regolith. All right, so these Apollo missions that I watched as a kid brought back about 840 pounds of rocks and soil. And of course, they were looking at them intensely in those early 1970s. But even today, people are still looking at these very same moon rocks, but with new technology, new instruments that didn't exist during the Apollo days. And so even though these rocks were brought back to the Earth over 50 years ago, we're still looking at them today with brand new technologies and new science instruments and making new discoveries. So we always talk about these rocks and these samples brought back from the moon as the gifts that keep on giving, right? Because as our technology improves, we can keep looking at the same rock and find out new stuff about it. All right, so the last, on all of the missions, 2 astronauts went down to the surface of the moon, and 1 astronaut stayed up in orbit and lived in this little capsule. And on the last 3 missions, on this capsule, there was a big bay, or like the back of a pickup truck, full of science instruments. And these science instruments looked down on the surface of the moon. So as the spacecraft orbited the moon, it was collecting science data. And so you can see, and during the Apollo era, we only stayed close to the middle of the moon or the equator of the moon, right? And so we had very limited knowledge. This is the near side, and I'm getting ready to show you where we landed, but you can see we had very limited knowledge of the moon, mainly around the equator. So here's where we landed, all on the near side of the moon, that face of the moon that we see all the time, all right? And we did that so we could have line of sight communications. We couldn't land on the far side of the moon and talk to our Apollo astronauts back then. So we landed on the near side so we could see them from the Earth and we could talk to them straight away. And Apollo 11, of course, we're getting ready to celebrate the 50th anniversary of Apollo 11. And here it landed in Mare Tranquillitatis, right? Or the Sea of Tranquility, right? And then there was 12, and then, oops, 13 is missing. I hope y'all know the story of Apollo 13. They didn't land on the moon, but we got the people back safely. So that was a great triumph. And then 14, 11, 12, 14, all the astronauts had to walk on their feet. By the time we got around to Apollo 15, 16, and 17, the astronauts had little cars to drive around. So that was really cool because we could get a lot farther. Now, some people think just because we've been to the moon that we've already done the moon. We don't need to go back to the moon. Been there, done that, right? So I want to dispel that myth really quickly. Turns out the moon's surface is about 90% of North and South America combined. So think about all of North and South America and maybe get rid of Florida, maybe the Baja Peninsula, pull off a little bit here and there. Most of, the surface area of the moon is equal to most of North and South America, all right? So let's say you are in charge of understanding North and South America, right? And there's where you landed on the moon. This is where you would have landed, all right? We'll start here in Houston. So those stars, are now been transposed onto the map of North and South America, but this United States, because Apollo 16 would be, say, right here at the Johnson Space Center in Houston. Well, the farthest we would have sampled and visited would be Apollo 12 out by El Paso. The farthest north, Apollo 15 right in the middle of Kansas. The farthest east, were Apollo 17, Memphis, Tennessee. And then Apollo 11, the first landing somewhere here in the swamps and forest of Arkansas and Louisiana, right? So if you keep the geometry of the landing sites on the moon the same, and you bring it to the Western Hemisphere, this is where you would have landed. And if this is where you would have landed, what could you tell me about the Appalachian Mountains over here, or this big thing called the Rocky Mountains, right? The Great Lakes, or these mountains here over in Washington where you have smoke coming out of them, volcanoes. We know there are volcanoes all along the west coast of the United States and Mexico, and also down here along South America. We now know those volcanoes are created by plate tectonics, right? And maybe you've heard about the Ring of Fire, or the Pacific Rim, you know, the Ring of Fire. Well, you know, that's we're part of it over here on the west side. We would not know about plate tectonics if this is all we studied. And say you don't really care about rocks and geology, you're kind of bored of that, but you really love biology. So look, you have got a lot of mosquitoes in Houston, maybe some swamp creatures there. But what about the Florida Everglades or the Okefenokee Swamp? I don't know if you've ever been to Olympia Peninsula up in Washington. Absolutely fabulous. And way down here in South America, the Amazon rainforest, right? So much biology diversity you wouldn't have a clue about if this is where you were only confined to. So the whole idea of been there, done that to the moon is, you know, I just don't believe that. All right, so after the Apollo guys, we sent a bunch of astronauts to the moon. Robots are cool because they're not large, so we don't have to spend a lot of money on them. They don't require air, food, and water, and they don't have a family they have to come home to, right? So they're a great bargain. And a lot of people don't realize that before Neil Armstrong even stepped on the moon, we sent 13 robots to the moon first to make sure it was safe. We used cameras from orbit to figure out where to land, and then we used Surveyor to make sure we could land there safely, right? And then all through the 90s and up until now, I got to put Chang'e 4 on there. There's been like a renaissance of robotic missions to the moon by all sorts of nations, all right? And look, we put these robots in polar orbits, and remember those Apollo orbits right at the equator, and we had very limited knowledge? Now look, the orbits go from the North Pole to the South Pole, around and around the moon, and now we're getting global maps of what the moon is made out of. And we're finding out that that area where we landed with Apollo is very unique and different from the rest of the moon. So it's really good, you know, that we're getting a global understanding. Before we went to the moon, we had three main theories about how the moon formed, where the moon fission, where the Earth split off from the Earth, the moon split off from the Earth because it was spinning fast, capture theory because the moon was flying through space and Earth's gravity pulled it in, condensation theory where the Earth and the moon kind of condensed together in the same neighborhood. Daniel Osborne was a student that did this, and I think it's really clever. But again, we're pretty sure, we're not quite, you know, we don't know first exactly, but we're pretty sure a Mars-sized thing smashed into the Earth and created the moon. And that comes from all the data and the rocks that we brought back, right? We think the moon had a magma ocean of several hundred kilometers thick, and eventually the magma ocean cooled on top and cooled on bottom to create the crust, mantle, and core, just like we have here on the Earth. And another thing we're finding out now is there are meteorites from the moon right here on the Earth. We go out, NASA goes out to the South Pole every year, and we look for meteorites on the white snow or the blue ice, and these meteorites are teaching us about other parts of the moon that we didn't land with Apollo. Problem is you never know where any particular meteorite came from. But the data itself is valuable, right? And so these are databases you can go to find out more about all of these lunar meteorites. There's several hundred of them now, all right? So here's how we see the moon at night. Well, we see the near side. We never see the far side, right? And this is kind of how a geologist will map the moon, where all these different colors represent eras or times from the oldest times going back 4.5 billion years ago to the youngest times, you know, even happening today. So you can see all the bright yellow craters are brand new craters, and then the greens are less old. And when you look at the browns, you'll see the oldest parts of the moon. So that's kind of how a geologist looks at the moon, right? And even though we went to the moon with Apollo, look at all these places that scientists still want to get back to with either robots or people. And we have so many questions, you know. Over here on this side are different types of rocks that we would like to sample. And you can see they're both on the front side and the far side. All right, so the latest visitor to the moon, I can talk till 3:10. Okay, great. The latest visitor to the moon was China's Chang'e 4 mission. It actually landed on the far side of the moon. You guys can watch this on YouTube or you know, go to their websites. But they have a lander, landed in January. It's still active. So they go to sleep at nighttime because the sun goes down. It gets very, very dark. So the lander and the rover called U-2-2, because U-2-1 and a lander identical to this one was the Chang'e 3 mission that landed about 5 years ago, right? So both the rover and the lander are working really well, and this is the first robotic mission to the far side of the moon. So the Chinese beat everybody else to the far side of the moon, so great for them. All right, but they're not the only ones. Look at all these other countries talking about going to the moon. So we're going to go back, and so we're going to talk about that later, but Russia and Europe are talking missions. India, Canada has some robots they would like to drive around. South Korea, Japan, all right. A lot of the spacefaring nations have their sights set on the moon in the next 10 years or so with robots, all right? So in the U.S., the approach we're taking is work with commercial companies, just like, Amazon delivers things to your house, or UPS and the big brown trucks brings packages to your house. We have companies that are set up now that are going to deliver things to the moon for us, so NASA doesn't have to, design the lander itself anymore. We have companies that like to do that. And not only will NASA fly to the moon on these landers, but any customer can do that. If your schools have something you want to fly on the moon and you happen to have the money to do it, you could fly something to the moon on these commercial companies. So it's a great partnership between our government agency of NASA and these private companies in developing these systems. And you can see, if one lander doesn't quite work so well, we'll have several to choose from. All right, so hopefully it's going to be very competitive, and we're going to have lots of companies making money and getting to the moon, but also lots of workers learning how to do this for all these companies. All right, so this is the United States space policy. All right, and what we're following right now is called Space Policy Directive 1. And the important parts is commercial. We're going to do it with commercial and international partners. I just talked about the commercial partners. And then as you saw on those other slides, a lot of other countries want to go to the moon. So we're going to work with partners to get back to the moon. And we're not just going like in Apollo, stay for a couple days and come home. We're actually going to go to the moon for long-term exploration and utilization of the natural resources there, all right? So Space Policy Directive 1 kind of gives us our marching orders. And just recently, Vice President Mike Pence, who leads the National Space Council, really put a challenge to us because he said, we want the first American woman and the next American man to land at the South Pole of the moon by 2024. Well, that's only 5 years away. So we're working pretty hard, all right, to get the plans together to allow this. And we're also working with our commercial partners because they may be able to do this. And then our American astronauts ride to the moon in commercial vehicles. Just like even though I work at NASA here at the Johnson Space Center, I don't fly a NASA jet to NASA headquarters, right? I fly commercial airlines. And hopefully that's the way we'll get to the moon with our commercial partners, right? The challenge will be just because a president says something, right? Congress doesn't always agree. So throughout the history of NASA, the presidents have given us our strategic direction, but then it's up to Congress to pay for this and write the bills that become law and give us our budget, right? And if the president and the Congress are agreeing on something, we move pretty well. If the president and Congress don't agree, well, things then get kind of, stopped. So we're going to have to see if Congress is really behind what the presidential administration right now is trying to do, right? Because it's been a mixed bag throughout history of the president and Congress working together, or the president and Congress, not so much seeing eye to eye. But it's up to the politicians to do all this, right? NASA would love to be in charge of its own destiny, but we're not, right? It's the politicians in this country who are in charge of NASA's destiny and kind of tell us what we're supposed to do and how much money we have to do those things, all right? So this focus on the South Pole. Well, why the South Pole? Well, most of the moon gets to see sun for about 2 weeks, and then you have darkness for about 2 weeks, right? And so to try to make it through a lunar night of 2 weeks long is really hard to do because you have to have batteries or fuel cells or something to keep you warm and keep you going electrically, right? But at the poles of the moon, there are areas that see the sunlight almost 90% of the time, all right? You can see these bright areas of highly illuminated placement at the poles of the moon, and this is the South Pole. And the reason that happens is you look over on this chart, the moon's axis of rotation is only tilted by 1.5 degrees. Now you know that our axis of rotation is 23.5 degrees, so that's why we have seasons, right? When your hemisphere, so we're here in the United States, when the northern hemisphere is pointing at the sun like it is now, we get hotter and hotter and it's summer, right? But when the northern hemisphere is pointing away from the sun, it cools down and we go through our winter. Well, the moon doesn't really have that, right? But what this does do is at the poles of the moon, the sunlight is almost going right across to the surface or parallel to the surface, all right? So if you have a crater on the moon, you have a hole on the moon, like this guy right in the middle, that Shackleton crater, that sunlight is going right across the top of your hole and it never gets there. So we have permanently dark, permanently shadowed craters in the polar regions of the moon, all right? Right next to areas where there's lots of sunlight, like 90% of the time sunlight, where we can have solar rays to generate power for us in our systems, right? Well, what's so cool about those, cool, no pun intended, about these dark places on the poles of the moon? Well, here's a map of them, so maybe you can see them a little better. So the North Pole here on the left, the South Pole on the right. So you can see all these red, permanently dark craters. The cyan color or turquoise, those are smaller permanently shadowed regions, all right? So they're all over the place. And we have evidence from orbit that inside of some of these permanently shadowed craters, there's water ice, both at the South Pole and the North Pole, all right? But we're focusing on the South Pole. Matter of fact, Shackleton crater, the rim of it is kind of right on the South Pole there, but you can see there are areas where we see water ice in these permanently shadowed craters. So what a great resource for us, water. You know, in this lunar desert, we have these oases at the poles of the moon with water ice. And just like the oases and deserts here on the earth, on the hot deserts of the earth, you know, travelers for centuries have seeked out these oases for water to sustain them. Well, this water on the moon can also sustain us, all right? And so that's why we're going to the South Pole. We have the highly illuminated ridges and crater rims where we get lots of sunlight, and they happen to be next to deep, dark holes full of water ice that we hope to mine and turn into water so we can drink the water. We can split the hydrogen from the oxygen. We can breathe the oxygen, and then hydrogen and oxygen can be used as rocket propellants. So what a great resource for us. All right, so the main goal of going back to the moon is to learn how to work and live on another planet. Here's kind of a polar region where there's not a lot of sunlight. You can see lights lit up by electricity, by tall solar arrays, mining going on with people and robots. We're going to be using the natural resources on the moon to live off the land, so we don't have to bring everything with us from the Earth. It's very expensive to launch things from the Earth because of our gravity. So if we can learn how to use the resources on the moon and live off of the land, we now can, do it in a more economically sustainable way. So living off the land, using the resources is critical for any long-term, presence there. And finally, we're going to use the moon as a proving ground. So if we can learn how to work and live on the moon, we can take all those technologies and all that knowledge to then work and live on Mars or other places in the solar system. So the moon is kind of our training ground. And the cool thing is it's only about 3 or 4 days away by rocket travel. So we can go there anytime we want. And if something breaks down, we just come home and figure out a way to fix it and then go back to the moon, right? It's not like Mars where it takes months and months to get there. And you can only travel back and forth between the Earth and Mars once every couple of years, right? The moon is there all the time. So it's a great proving ground for us. All right, so that's it. So, I don't do a very good impression of Yoda, but I think if Yoda from Star Wars was talking to us about the moon, he would tell us close, interesting, and useful the moon is. All right, and so that's it. I hope you all enjoyed that.
You can do stop sharing.
And we're going to do stop sharing so I can see everybody and we can take questions.
Yeah, thank you so much. That was really interesting. Appreciate it. I'm going to let Tedrick take over the question. So he's going to start reading them out, right? You good,
Yeah.
Tedrick?
Yeah. Can everyone hear me?
Yes,
Yep.
and I'm going to lead the show, and hopefully I don't kill everything. So,
All right. So we had some pretty good questions so far. So if anyone has more, feel free to ask. But I want to start off with actually a jumble of questions because there were a lot of them right along the same line. So what do you love your job? And what's the scariest, most entertaining, and weirdest parts of your job?
Yeah, I do love my job because, you know, I started out as an engineer, I became a scientist, and I learn something every day when I come to NASA to work because I work with so many different people, so many different backgrounds, and read so many different science papers. I'm always learning something new. You know, someday I think my head's going to explode, but it's a great place to work, right? So I don't know about weird. I'll have to think about that one. But one of my most fun projects was back in the 90s, we were working, you know, I talked about growing plants. And we were working on developing a slow release fertilizer substrate that we would take with us to the moon or Mars. So we not only use in the soils to grow plants, but also we use the slow release fertilizer to kind of kick it off. So we call it zeoponic substrate. So for about 8 years, I was a space farmer, learning how to grow food in a life support system where everything is recycled and reused. So that was a lot of fun. And if I can think about weird, well, maybe it was the alien. Yeah, I can't talk about that one. Okay, next question.
All right. Let's see. How long is considered long-term exploration?
Well, that's a good question because there are a lot of people at NASA and also in this country that want to just forget the moon. You know, yeah, we went to the moon. We have moon rocks. We can send robots to the moon, but we want to send people to Mars, right? That's what we really want to do. So the more time we spend on the moon, the more we push Mars further out into the future, right? And so different people have different definitions of long-term exploration and utilization of the moon. For me, it's forever. I mean, you think about how mankind has spread all over this planet from continent to continent, and once people got to a place, they pretty much stayed there, right? And they learned how to live off the land. They learned how to trade with partners, you know, whatever. So I think of long-term as indefinitely. Some people think of long-term as 10 years because, boy, we really want to get to Mars, right? But if mankind or humankind is ever going to expand off of the Earth, we're going to have to learn how to use the resources. The private companies are going to have to get involved so they can, you know, make money and generate economy and just, you know, that will spur things on. You think about how the United States has grown over the centuries. It's because of the economic engine that has been driving it all. So long-term can be different things to different people, but I hope once we go, we're always there.
Thank you. All right, so next, sounds like we have a question from Elizabeth, and then we'll have a question from Quincy. So Elizabeth, go ahead and unmute yourself and ask your question.
So I was wondering, how do you build your rocket ships?
How do I build my rocket ships? Well, that's a good question. So if you look behind me, that rocket that I built didn't go so well, right? It's bent. It's kind of crashed. So building a real rocket, building real spacecraft requires lots of different people because it turns out these things are very complex, have lots of moving parts and lots of systems. So you have to have a team of people to work on the structures to hold the thing together, or the propellant experts to figure out which propellants you're going to use, you know, what kind of tanks those propellants go in, how cold they have to be retained to keep the propellant in a liquid form. The electronics people have to, you know, design things so the astronauts can talk back to the Earth, the spacecraft can talk to itself. So it, you know, it's very complex, but it starts off with an idea, right, or a sketch. And you think, okay, I want to build this thing, and you have to think, well, what does it need to do? So we call those functional requirements, right? So what are we trying to do? What functions or capabilities do my spacecraft have to have? And then once you write down what you want your spacecraft or rocket to do, then you start saying, well, okay, well, how much, right? How big do you want? How much do you want this rocket to lift off in the Earth? How fast do you want your spacecraft to travel to Mars? So once you know your functional requirements of what you want to do, then you start getting into your design requirements to say, well, how much do you want? How fast do you want to go? How many people? All those kind of things. So it starts off with, an idea, and your functional requirements turn into design requirements. And then somewhere in there, you have to develop what we call a concept of operations of how you would even use all this stuff, right? So usually it's, what do you want to do? How are you going to do it with a concept of operations? And then a design process. So those are the three basic steps in system engineering.
All right, I think next we have a question from Quincy.
Hello. My question is, if you had to choose only one item from the ISS that is most important, not the ISS itself and not the wires, what would you choose?
The one item. Well, so that's tricky, right? Because I love the high definition cameras that are on ISS that look down on the Earth, so we get fabulous images of what's going on here on the Earth. But without those big solar arrays generating electricity, our astronauts couldn't live there, right? So my engineer half loves the solar arrays. My science half loves the cameras. How's that?
That's good. All right, next I think we have a question from, I will try to say this right, but I think it's Stanky Elementary. Stink?
What is the coolest rock you've ever found?
The coolest rock? Oh, man, there's so many of them.
On Earth or the moon?
Okay, well, I've never been to the
On
moon.
the
moon. I think one of the neatest rocks we brought back from the moon was on Apollo 15, and it was called the Genesis Rock, right? Wasn't it Apollo 15?
Yep.
Yeah, Apollo 15 Genesis Rock. And that was the first real big sample that was from the bright highlands of the moon. Remember in the talk, I talked about the old highlands and the young mare or lava flows. Well, that Genesis Rock really gave us an idea of how old the highlands are, right? So if I had to pick my favorite moon rock, it would be that, but I never give one answer. So my favorite dirt, or soil on the moon was from Apollo 17. They actually found orange colored soil, right? So you look at the moon, it's all gray, right? But they actually found orange soil on the moon, and it turns out orange stuff was actually small glass spheres that were created in a volcanic fire fountaining eruption. I don't know if y'all watched in Hawaii last year when the eruptions were going off, and unfortunately the lava was covering up the neighborhoods. But boy, was it beautiful to watch at nighttime when all that stuff would go up in the air. Well, we had those same kind of eruptive fire fountainings going on the moon, and that orange soil is really cool stuff.
All right, and next I think we have a question from Seth.
When would you say your next Apollo mission would be?
Well, Seth, the vice president and the National Space Council has challenged us to get there in 2024. So that's only 5 years away. It's going to take money to do it because, you just have to hire people and work really hard to get something built in 5 years. But certainly we'll have the next people, on the moon within the next 10 years. So before the vice president challenged us with 2024, we are looking at the year 2028. So within the next decade, I think you'll see the first people walking on the moon. Now, again, that only goes if Congress agrees with this presidential administration to do that. But whether the United States goes to the moon or not, those other countries are going to go to the moon. China is going to be on the moon. Europe is going to be on the moon, right? Probably either with us or with China. I don't know that Europe will do it by themselves, but there will be some kind of humans on the moon within the next decade. I hope they're Americans.
All right, next I think we have another question from, I believe we have a question from Quincy. Or did I skip Liam?
No, I'm going
Okay.
next since it was Seth. And then, yeah. What is the grossest thing that astronauts have to eat in space?
Oh boy, I don't know, because I've tasted some of that food over in the food lab, and it's actually not that bad. So one of my hobbies is taking Taekwondo, right? I started that when I was 53 years old. I sure wish I would have started sooner, because my old body doesn't like to kick and bend and punch like a little youngster. But the guy that teaches us, our master in our Taekwondo studio, Stan Love, is an astronaut. I've never really asked him what the grossest thing he had to eat. But, just like you at home, you probably wouldn't eat it if it was gross, right? You would just kind of shove it aside and tell mission control, yeah, we ate our kale, all's good. So I can't really tell you, because I have, I only eat the astronaut food that I can buy at the gift stores and what I've tasted at the food lab. And I know one thing they do like to do is they like to spice it up. So the shrimp cocktail, really tasty, right? But they bring up M&Ms and all sorts of candies and stuff. But I don't, before astronauts go into space, they work with the food lab so that the food lab gives them the kind of food they like to eat. We're not going to send an astronaut up there and then make them eat gross food. They're going to eat food that they chose.
All right, thank you. So yeah, now we have a question from Liam.
Have you planted plants with the moon soil?
No, Liam, I've never got to do that yet. When in some of our tests in the 1990s, when I was a space farmer, we used what we call simulants, simulated lunar soil. So we know, bringing the rocks back from the moon, we know what they are, and they're very similar to rocks here on the Earth. So you can take rocks on the Earth and smash them up into powder to make it fine like a lunar soil, and then grow plants in that simulant. The same thing with Mars. We know from our robots on Mars and also the meteorites that have fallen on the Earth that have come from Mars. We know how to make simulants of the Martian dirt or soil, so we can grow plants in that also. But back during Apollo, that was one of the scary things. They weren't sure if this dirt and these rocks coming back from the moon was going to infect anybody or do something really bad to the biosphere on the Earth. So they did. They grew plants in real moon dirt back in the early 70s. And they actually fed moon dirt to rats and all sorts of things. And everything lived. No dead rats, no dead plants. So they found out there's nothing toxic on the moon, so we don't have to keep our astronauts in quarantine every time they come back from the moon. So that was probably the last time anybody ever grew plants in real moon soil. Hopefully, we send our robotic missions to the moon with our commercial partners. We bring back materials from the moon, and we can do that again with new plants and new people like you guys.
Okay, so next up, I think we have another question from Quincy.
I was a part of the FLL, and our project was basically calming astronauts with the color pink. We heard that you painted the walls of the ISS like a salmon-y color to calm astronauts down. Have you guys thought of doing anything further with trying to calm them down?
Well, I do have some friends that work in what's called human factors, right? And so it's the human factor people that make sure, you design something that's livable, right? Now, sometimes you look at the space station and you wonder if it's really livable because you have wires everywhere and instruments everywhere. But yes, they tried to pick those calming colors or warmer color. Now, matter of fact, the Gruener household is a mess right now because we're redoing everything. And we're picking, my wife's a school counselor, so we want warm, nurturing colors. And we do the same thing inside of our spacecraft, right? So, you know, I'm not an interior designer, so I can't tell you which are the best colors to make people the happiest and calmest. But, you know, you can look at my wall here and it's just kind of a beigey color. But I think they went with more blues and grays on Space Station versus the good old beiges that have been around forever.
Okay. Next, we have another question from Elizabeth.
So, do you know when you're going to be launching your next rocket ship?
When are we launching our next rocket ship? No, I don't really keep up with that, you know, on a daily basis. You can go to the Kennedy Space Center or Cape Canaveral website, and they have a listing of all the rockets that are coming up because there are so many of them going up now. You know, it used to be when I was a kid that everything that launched was a government mission. Whether it was NASA or the Department of Defense, it was all government missions. And then the private industry started getting involved. So, you know, maybe some of you guys have satellite TV in your house, right? Well, that's a private company that's beaming those satellite TV channels to your house. Telephone communications, weather forecasting and images of the weather. All of those are done by commercial businesses and companies. And it was about, I think maybe 8 or 9 years ago or 10 years ago, where the number of commercial missions to space actually got higher than the number of government missions. So now we're launching more commercial stuff in this country than we are government stuff, and it's really hard to keep up with, you know, when the next communication satellite goes up or what. But, you know, you can go to Cape Canaveral. They have a schedule of launches. At NASA page, I'm trying to think, you know, when do we have a mission coming up? And I'm scratching my head and coming up blank. We always supply the space station. So every 3 months or so, another rocket goes up to bring food and groceries and air to the space station every 3 months or so. And that's on SpaceX or Cygnus.
And I think it was like May 5th where we just sent up a latest SpaceX resupply mission, including one of
That's
our,
right.
our Hermes experiment. That
Right.
went
So
up
we
there
have
as
we have
well.
coworkers who sent an experiment up to space station on the launch that was just a week ago. So if you like to watch launches, go live in Florida because then you get to watch all sorts of stuff going to space.
All right. Thank you. Next up, I think Quincy's brother had a question. Did you want to ask his question for him?
Yeah. How is the Wi-Fi situation, like the internet stuff going on the ISS?
Pretty well. You know, that's a challenge because you have all these modules, long line of modules, and they go in different directions, right? And so you can't just keep a wire on everywhere you go. So they're finding out there's not a lot, you know, that they design their systems correctly, number one. First, you have to understand what they call the, you know, electromagnetic environment. And once you understand that, you can design your systems to work well, and we've had a good, you know, response. Now, when we get to the moon, we were just talking about that today, as a matter of fact, down the hall. Will Wi-Fi really work on the moon? Because the moon's a very harsh radiation environment. The space station is inside, you know, our magnetic field and Van Allen belt, so they're somewhat shielded from all the radiation that's really out there in space. But when you go to the moon, man, you're getting hit hard by the radiation from the sun and what's called galactic cosmic rays, which come from all over the universe. And so we were talking about, well, how's Wi-Fi going to work on the moon? Because you have that huge radiation environment, and is it going to disrupt your signal? And we decided, yeah, there's going to be a little bit of static. You know, it's not going to be crisp and clean, but you're going to have your receivers and your transmitters really shielded so they work well with the signal. But as the signal goes from one place to another on the moon, it's going to get a little bit messed up by all that radiation. But it works well on the space station.
All right. So let's see. I want to check around because I know we've had a lot of questions from a few people, and they've been really good questions. And I want to see if anyone else has any questions that hasn't piped up yet. I can't see everyone on my screen, so if I can't see you, go ahead and just put your question in the chat, and I can either ask it for you or I can call on you.
All right, so Tedrick Page just told me in the chat room, somebody asked how long I've been working at NASA.
Yeah.
So I was just kidding when I showed you that picture of me when I was 5 years old. That really wasn't my first day on the job. I went to college just like, you know, a lot of people do. And I started working here at the Johnson Space Center in 1986. All right. So here we are in 2019. So I'm on my 33rd year. Going on to 34 and then 35, 36, 37. And hopefully by the time I get up to about 38 years at NASA, we're going to have people on the moon. So it's been a while, but it's been fun. Otherwise I wouldn't be around. You know, I would go find something else to do.
All right. And I think we have another question from Quincy and then a question from Seth.
Do the astronauts on the ISS, this is kind of like a holiday thing, like, do they do anything special for Halloween? Like, do they dress up or do they, like, have any candy? Do they just, like, acknowledge it and not do anything?
No, you know, you're a human, right? You're up there. And so, yeah, all the different holidays, they try to do something fun. I know when they send up the modules with supplies, you know, they always try to put some presents in there for them. But, you know, that's going to be the challenging thing, you know, for humans who are actually working and living on the moon someday or traveling to Mars, right? Typically, a Mars mission requires 3 years. So you fly out to Mars about 6 to 8 months. You spend about 1.5 years on Mars, and then you fly home in about 6 to 8 months. So you think about that. Your little mission to Mars, there's going to be about 4 of your buddies with you. Well, hopefully you're buddies because you're stuck together. But for those 3 years, you miss 3, you know, baseballs. I love baseball. So you miss 3 baseball seasons and going to baseball games. You miss Halloween. You miss Thanksgiving and being with your family. You miss the Christmas holidays. So they try to do all that as much as possible up in the space station to keep the spirits up. But the tour of duty, most astronauts only spend 6 months up on space station right now. You know, so if you plan your mission correctly, you're home in time for Halloween if you have a sweet tooth, right? Or you're home in time for Thanksgiving so you can spend it with your family. But so right now our astronauts on the station, you know, they miss 6 months of what's going on down on the Earth. But when we do get to the moon for that long-term settlement and, you know, multi-year missions to Mars, it'll be interesting to see how people react, you know, from an emotional and psychological point of view.
All right. So real quick, because I think we are reaching the end of our time, and I think Zoom actually might cut us off. So in case it cuts off, first of all, I want to thank everyone that was able to join us.
Yeah, this was a lot of
I
fun.
hope you were able to learn a few things along the way, learn some good stuff from John. And I hope your challenge is going well. Now, I did promise if we can fit you in before it cuts off, we'll have Seth ask a question, then we'll have Haley ask a question.
All right, speed round.
So when are you going to launch your next satellite?
Launch our next satellite. Well, Seth, you know, somebody asked about our next launch, but and I wasn't quite sure. So go to your browser on the internet, type of Cape Canaveral launch schedule, and you'll see when we do that. Of course, the Europeans are launching things all the time, the Chinese, the Russians, a lot of stuff going into space these days, but I don't really know when we're launching our next thing.
And our next probably mission that we'll be involved in is Mars 2020, which will launch next summer. I don't know if we have any missions we're involved in before that, but at least Mars 2020 maybe.
So hopefully you heard Paige in Mars 2020. That's a new robot, kind of like Curiosity, heading to Mars to do more cool stuff.
Yeah, and also I think Mary put a link to space.com calendar that keeps track of all sorts of things going on in space, including launches.
Cool.
So, yeah. All right, let's have our last question from Haley.
How about Seth?
So I was wondering, how long has one person been in space for?
All right, so the longest somebody has been in space is a Russian, all right? and I forget his name, and he spent over a year up there. Now, you know, here in the United States, there was we had these twin astronaut brothers, right? The Kellys, Mark Kelly and what's his
Scott Kelly.
Scott Kelly. So Mark Kelly and Scott Kelly. Now, what a cool science experiment. You have twins, right? They're the same. Let's put one in space and see how he gets different from the buddy that stayed on the Earth, or the brother that stayed on the Earth, right? And Scott Kelly, he didn't quite make a year. It was more like 340 something days, right? But that's the longest an American astronaut has been in space, about 340 something days. But there has been a Russian that has been up there for just at a year or a little bit longer than a year. But, you know, that's one of these big challenges. I keep talking about how our missions to Mars are going to be multiple years in length. And so what happens to the human body when we don't have the gravity of the Earth, right? And what happens to our bones and our muscles? And is the gravity on Mars going to be enough to, you know, counteract all of that? Or the gravity on the moon? So the moon's gravity is about 1/6 of the Earth's. So you feel like you weigh, you know, if you do weigh 100 pounds on the Earth, you would feel like you weigh 16 pounds on the moon. Well, is that enough? Is that enough weight to work your muscles and to work your bones so the bones don't decalcify, the muscles don't atrophy, right? So that's why the space station is a pretty good test bed for human spaceflight, just like the moon's going to be a test bed or a proving ground for living and working on planetary surfaces. And we hope to find out what happens to the human body as it spends years on the moon. But we're not there yet.
All right. Thank you, John.
Yeah.
So it is about time we should wrap up. I did see a question that led really well into when is the next one of these? So the next session we'll have like this is in 2 days, May 16th. It will be at 1:30 p.m. Pacific time or 3:30 p.m. Central. And we'll be chatting with George Grosby from NASA Ames. He's an engineer there. So, so I guess if we can have everyone, if you want to unmute yourselves and everyone say thank you to John.
Thank you.
Yeah, it's been fun.
Thank you. Thank you.
All right, and
This was an amazing
John, I don't know if you had any other words you wanted to sign off with, or
This was a good experience.
Yeah, I agree.
thank you.
I'm unmuted.
And now everyone's unmuted and we're getting feedback. So we'll go ahead and thank you so much.
All right, I would definitely
Thank
do
you,
that again
too.
because it's quite interesting.
Yeah, same.
Bye.
I would probably do that again.
Bye.
Everything seemed kind of cool.
And that'll take you out.
We're slowly going to be removed. Slowly but surely.
Bye.